In the race to build bigger, crazier, more complex AI, we're always hearing about the next giant model. But what if the biggest breakthrough wasn't about adding more complexity, but taking it away? Today, we're going to look at a really cool approach to AI image generation that basically throws out the old rulebook. It suggests, a radically simpler way to get those amazing pictures we're all seeing. So let's start with a kind of weird question. How do these powerful AI image models actually do what they do? You'd think, logically, that they learn to predict the final picture, right? Well, the strange truth is, for years now, the very best models have done the exact opposite. They learn to predict random, static-like noise. I know, it sounds totally backward, but that's been the secret sauce. The real question is it actually the best way to do it? Okay, let's get into this whole denoising secret. For a long time, the #1 technique had this fancy name, epsilon prediction. But hey, don't let the Greek letter fool you. Epsilon is really just the symbol engineers use for that random noise. So what this all means is that the AI's entire job, its whole purpose, is to look at a fuzzy, staticky image and just guess what the noise part is, not what the picture's supposed to be. Yeah, the process is kind of like a sculptor chipping away at a block of marble. You start with just pure noise, total static. Then, in these tiny little steps, the AI model predicts a small piece of that noise and just subtracts it. And it does this over and over again. Slowly but surely, a clear image starts to emerge from all that chaos. The models that first figured this out, called DDPMs, they found that this weird method of predicting the noise actually gave them much, much higher quality images. And just like that, it became the industry standard. Right, so to really understand why predicting noise might be, taking the long way around, we need to talk about a really core idea in machine learning. It's this concept that all realistic images, they live on something called a manifold. This sounds complicated, but I promise it's the key to unlocking a way simpler approach. The manifold hypothesis is actually pretty simple but super powerful idea. Basically, it says that out of all the trillions upon trillions of ways you could possibly arrange pixels on a screen, the combinations that actually look like real-world things, photos of your cat, a car, a landscape, they make up a tiny, tiny fraction of the total. They all follow certain patterns, certain structures. They all lie on this relatively simple surface inside a just impossibly vast space of possibilities. Okay, let's use an analogy to make this super clear. Imagine a gigantic room. A mind-bogglingly huge, high-dimensional room. This room represents every single possible way pixels could be arranged on a screen. Now, floating somewhere in that massive room is a single, crumpled sheet of paper. That paper is the manifold. It's the tiny little area where all the pixel combinations that look like real stuff to us, faces, trees, dogs, actually exist. And everything else, all that empty space in the rest of the room, that's just meaningless random noise. So this brings us right to the problem with the standard method. If the AI's job is to predict the noise, we're basically asking it to learn the coordinates of every single point in that massive, mostly empty room. It's an impossibly huge task, especially as the room gets bigger and bigger with higher resolution images. And this slide really breaks down the two different jobs we can give the AI. On the left, you've got the old way, predicting noise. That forces the AI to learn a map of the entire vast room. But look at the job on the right. What if we just asked it to predict the clean image itself? This is called X prediction, where X is just the final image. In our analogy, this is like telling the AI, hey, forget the room. Your only job is to find the paper. It's so much simpler, so much more focused. And here is the hard data that proves it. Researchers tested this whole idea on a standard image dataset. They measured the quality using something called an FID score. Just think of it like a golf score for AI images, where lower is better. Now look at this. When the model was tasked with predicting the image directly, that's the XPRED line, it got a really good score, 8.62. But when they gave that exact same model the job of predicting noise instead, it was a complete disaster. A score of 372 isn't just bad, it's total nonsense. It's the AI equivalent of just a garbled, unrecognizable mess. The model just got hopelessly lost in that big, empty room. And that's really the bottom line here. When you're working in that massive, high-dimensional space of pixels, asking a model to map out all the possible noise it's too much. The model just doesn't have the capacity to navigate all that emptiness, so it just breaks down. So this leads us to this beautifully simple solution that was kind of hiding in plain sight the whole time. Instead of trying to make our models bigger and beefier to handle all that noise, what if we just gave them an easier job to do in the first place? And this is the real aha moment. What if we just stopped asking the AI to do this ridiculously complex task of mapping all the noise? What if its only job was the one thing that actually matters? Finding that crumpled sheet of paper in the room. The researchers behind this idea did exactly that, and the name they gave their model is just perfect. It reflects this beautiful simplicity. They call it just image transformers, or JiT for short. It's a pretty standard vision transformer that's an AI architecture that's great at seeing patterns, and it works directly on the pixels with just one simple goal: predict the clean image. That's it. And to really get just how minimalist this is, look at all the complicated machinery it doesn't need. There's no complex image tokenizer, which is kind of like a special dictionary for pictures. No pre-training on other giant models. No extra guardrails or fancy loss functions to guide it. Nope, it is a completely self-contained system that just learns one thing and one thing only: how to find the clean image. Okay, and this part is maybe the most surprising proof of all. The researchers actually tried to make their network less powerful. They added a bottleneck, forcing it to compress all the information it was seeing. And guess what happened? The performance actually got better. This is such strong evidence for that manifold hypothesis. Because that sheet of paper is simple and low-dimensional, the network doesn't actually need a massive pipeline to find it. A smaller, more focused network does the job even better. So, let's talk about what this all means for the future of AI. This research really proves that simpler can absolutely be stronger. It opens up a new, way more elegant and self-contained way of building these generative AI models. Don't think for a second that simple means weak. When they scaled this JET model up, it achieved an incredible FID score of 1.78 on high-res images. I mean, that score puts it right up there with much, much more complicated multi-stage systems. It's simple, it's elegant, and it performs at a state-of-the-art level. And why this matters goes way beyond just making cool pictures. By creating a simple, self-contained system that isn't totally tied to the messy specifics of images, you could apply the same approach to other incredibly complex problems in science. Things like predicting how proteins will fold, designing new molecules, maybe even forecasting the weather. So it really leaves us with this powerful question, doesn't it? In a field that is obsessed with scale and complexity, this shows that sometimes the most elegant solution is also the simplest one. It really makes you wonder, what other huge AI challenges are we maybe overcomplicating when a simple return to the basics might be all we really need?